This video is for the skills practice 50. For number 1, what is the pH of a 0.34 molar solution of HNO3? This is actually supposed to be HNO2. The Ka value that we would get from the back of the packet in our packet sheet is that the Ka for HNO2 is equal to 4 times 10 to the power of negative 4. So now we need to figure out the molarity of the H3O plus so that we can figure out the pH. So we need to do an ice table. HNO2 plus HOH gives you H3O plus and an NO2 minus. So what we're saying is that the initial molarity of HNO2 is 0.34 of HO3, H3O plus and NO2, it's 0. The change is going to be minus Y. Here it's going to be plus Y and plus Y. And the equilibrium, 0.34 minus Y. Here Y, there Y. And we're going to assume this minus Y is so small that it's negligible. So now we have the equation and we know the Ka value. So 4 times 10 to the power of negative 4 is equal to Y squared. This times this is equal to Y squared divided by 0.34. What we get for Y is that it's equal to 1.2 times 10 to the negative 2. And that Y is the H3O plus concentration, so they're asking for the pH, which means the negative log of that. And what we should get for the pH is equal to 1.93. For number 2, you would set it up in the exact same way. You're just going to use the Ka value that they already give you for benzoic acid. You'll find out what benzoic acid is on the back of the sheet. Just use this Ka value as opposed to the one in the back of the sheet. And what you should get for the pH of that is pH is equal to 2.33, and you're doing it the exact same way as number 1. For number 3, comparing the concentrations, why are weak acids called weak? Well, they're weak because they don't completely dissociate, meaning that there's still some of the reaction goes to the left, so that's why they're weak. And the relationship between a weak acid's Ka and the pH. So if you remember, Ka is equal to the concentration of H3O plus times the concentration of the A minus, which is just the conjugate base, divided by the acid, HA. And I'm just using H and A minus as sort of a generic acid. So if the Ka value goes up, then the H3O goes up as well, because it's on the top of that fraction. And if the H3O concentration goes up, and here's the tricky part, as it goes up, the pH actually goes down because it's more acidic. So if it's got a lot of H3O plus, then it's going to be a super acidic for the pH. And this makes sense because if we use some generic numbers that are off the top of our heads, so let's say 1 times 10 to the power of negative 4, well, the pH of this will be 4. But if the concentration of H3O is 1 times 10 to the power of negative 3, which is a bigger number than negative 4, the pH will be 3. So as this gets bigger, this gets smaller. So if we're trying to compare Ka and pH, then what we're saying is as Ka of a weak acid goes up, the pH goes down. And this makes sense because a Ka of a strong acid is really big, and the pH is going to be really small. So a strong acid like HCl will be around pH 1, 2, almost. Number 5, I'll write it up here. The pH is supposed to be 2.78, and it's done the same way number 1 and number 2 is. And number 6 is a little bit different. You have a 0.25 solution of unknown acid with a pH of 2.5. What is the Ka? So if you're given a question where you have the Ka being asked for, what we're going to say is we're going to assume that this number for the solution molarity and whatever we get from the pH as the hydronium concentration, those things are at equilibrium. So we're not going to go to a nice chart necessarily. So if pH is 2.5, we can figure out the concentration of H3O plus by putting 10 to the power of negative 2.5. And that should give us a concentration of H3O plus as being 3.6 times 10 to the power of negative 3. From that, we can figure out the rest of it. So if you remember on the ice chart, we have a generic one, HA plus HOH gives you H3O plus and A minus. Well, at the end, we found that this was Y and Y, and this was a number. Whatever the concentration of H3O was, that was also the concentration of the A minus. So if we find the concentration of H3O, then we did find the concentration of A minus. And this Ka over here would be just H3O plus times A minus divided by HA. So if we have a 0.25 molar solution, which is at equilibrium, we can pretty much start plugging things in. So we got 3.6 times 10 to the power of negative 3 times 3.6 times 10 to the power of negative 3 divided by the concentration of that solution, which is 0.25, and we should get the Ka as being 3.99 times 10 to the power of negative 5.